Okay, this is a solution to problem number 9 in the homework, which is when a quarterback is going to throw a ball to a receiver that is down the field. So if you look at the things that you know, okay, what you know is you have a quarterback that is throwing the ball to a receiver down the field. So a few things that you can assume is that the ball kind of starts and ends at the exact same height, okay? Because a quarterback throwing, wide receiver catching, they're going to be about the same height. Some things that you know, the quarterback throws it at an angle of 40 degrees, and we know that, or we don't know, what the initial velocity is that the quarterback throws it at. In fact, that is one of the things that we are trying to figure out is what velocity does the quarterback throw at. Okay, so there are a few issues here, okay, that we need to think about when we're solving this. We really only have one bit of information, and that is that the quarterback throws the ball a distance of 31.5 meters. Okay? So, if we think about what we know, okay, what we know is in the x direction. We know is 31.5 meters. And then we look to our equations in the x direction, which is x equals b initial x times time. Okay? So we're going to have to do something new here that we haven't done before. Okay? And that is, we're going to actually have to look at the equation for b initial x, which is b initial times the cosine of theta. And we're actually going to have to put this in for that. So x is going to equal b initial times the cosine of theta times time. Okay? Our only problem is we still have two unknowns in this equation. Okay? I don't know what this is, the initial velocity, and I have no idea how long it's in the air. So at this point, I have no way to solve this problem. So what we're going to do is we're going to look in the y direction and say, okay, what do I have in the y direction that might help me? Okay, and one of the equations I can look at is y equals b initial y t plus 1/2 g t squared. Okay, now a few things that I know about this equation is that y is going to equal 0. And the reason for that is because we start at y equals 0 and we end at y equals 0 if we choose our world this way. Okay, so we know that this term is going to end up at 0. Well, what does that do for us? Well, I can then take this term, the 1/2 gt squared, and bring it over to the other side of the equation. And yes, when I do that, it would be negative. Okay? And then I look at that and say, well, I still don't know what this is doing for me, but I'm going to get rid of time. So now I have minus 1/2 gt equals v initial y. Okay? And again, what I can do here is v initial y is v initial times the sine of theta. So I could substitute this in for that. So I have minus 1/2 gt equals v initial sine theta. But I still have too many unknowns. Okay? I still don't know what time is. I still don't know what that is. But we do have something that we do have in common with these two equations. And here's the trick to this particular problem. The trick to this particular problem is that this time and this time have to be the same time. So we're going to do some manipulating with this. And what we're going to do is I'm going to take this equation, and I'm going to mess with it over here for a little bit. So I have x equals v initial times the cosine of theta times time, and I'm going to solve it for time. So I'm going to divide both sides by v initial times the cosine of theta, v initial cosine theta, and rewrite this. So I have time equals the distance x divided by v initial times the cosine of theta. And then I'm going to do the same thing with this equation right here. I'm also going to solve it for time. I'm going to multiply both sides by 2, okay, and I'm going to divide both sides by g. So when I do that, I'm going to have time equals 2v initial sine theta divided by g. Okay? So, what did that do for me? Well, what that did for me is I now have two equations that have time in them, and these two times have to equal each other. Okay? The time in the x direction has to equal the time in the y direction. So that means this equation is equal to that equation. So I'm going to set those two equations equal to each other. So now I'm going to have x all over v initial cosine of theta equals 2v initial sine theta divided by g. And in case we forgot, what we're trying to solve for is I'm still trying to figure out what the heck v initial is. So somehow I have to take this equation now and I have to do some really fun algebra. Okay, so first off, I'm going to multiply both sides by g to get rid of that. And so this will be gx. And then I'm going to multiply both sides by v initial cosine of theta, which would cancel that. And I'm going to multiply this side by v initial cosine of theta. So now, what I have, is an equation that says gx equals 2v initial sine theta times v initial cosine theta. So, this times that is v initial squared, so I have 2v initial squared times the sine of theta times the cosine of theta equals gx. Now, what I'm trying to get is this term by itself. So I'm going to divide both sides by 2 sine theta cosine theta. And then I have to do the same thing over here. So 2 sine theta cosine theta. That cancels all of that. So what I have left is v initial squared equals gx divided by 2 sine theta cosine theta. Okay? And then essentially, since I want v initial by itself, I have to take the square root of both sides. So the initial velocity is the square root of gx divided by 2 sine theta cosine theta. And every single one of these terms I know. So I can just plug them in. So the square root of 9.8 times 31.5 divided by 2 sine 40 cosine 40 is equal to the initial. So, if you take out your handy-dandy calculators and do that math, you are going to come up with 17.7 meters per second. Actually do the math so you can see how it's done. Now, looking at this, I know I dropped a sign somewhere, but the signs work out. I made it on campus.